Okay, energy continued. We're going to just continue on, focusing a little more on energy itself after our talk about enzymes and how they regulate or how they change the energy of reactions. Let's find out what this energy actually is and what it's doing. So first of all, the first law of thermodynamics. Underneath all biology and chemistry lies physics. Physics is basically the study of the fundamental rules of the universe that make everything happen. And thermodynamics is basically laws about energy. And the first law of thermodynamics is something that's relatively common to you. You may have seen it called the conservation of energy. And it's the old thing when you were in elementary school where you said, energy cannot be created or destroyed. It can only be transferred from one form to the other. Okay? But what we really want to say here, and these laws are in your book, by the way. I'll go back and show you. They're on page 127. They say things in a little more grade 12-ish kind of way. They'll say things like, in a closed system. Closed system means there's no outside source of energy coming in or no outside loss of energy to the outside. So a closed system, in a closed system, they say that the amount of energy is constant. Okay? But that's something that we are familiar with. In other words, this is the basis for balancing chemical equations, right? If you have so many atoms going in, you have to have the same number of atoms coming out, even though they can be rearranged in different forms. Now, the other thing that's interesting, though, is the second law of thermodynamics, which is one that maybe you're not familiar with, and that's on page 134 if you're looking for it. And it basically says that second law of thermodynamics says that every energy change, or we called them energy transactions in our last video, right? We were comparing them to banks and finance. Every energy change involves a sort of a loss of a certain amount of energy, right? Involves a certain amount of unusable energy. Unusable. That doesn't look right. I think there's only an A in unusable. Unusable energy. There we go. Typically, this unusable energy takes the form of heat. And heat is basically jittery molecules. Molecules that have been all sort of broken down to the point where they're just shaking, and that shaking isn't doing anything useful. When you heat molecules, they shake. Shaking molecules doesn't really have any benefit. You can't gather their shaking and use it for anything useful. That's why we say that this energy is unusable. It's waste energy. So every time you do something in the universe, you change energy, and every time that happens, you lose a little bit. It's kind of like banking fees. When you have a bank, you go and you do a transaction, but now what banks do is they charge a small fee for that transaction, so that money is gone. It's also similar to changing your money into foreign currency. If you have $100 of Canadian money, you can go and buy so much American money. Now maybe that $100 would buy 70 US dollars, but they're not going to give you 70, they're going to give you 68 because there's a $2 fee for the transaction. So if you keep changing your money back and forth and pay a $2 fee each time, eventually you'll be out of money. So in the universe, there's like a fee for changing energy, which is waste heat. And you can't avoid it no matter what you do. It's a law of thermodynamics. And what this waste heat is it basically, another way of putting this law is to say that systems, well, I should say closed systems tend toward disorder. Disorder. And the word that we use to describe disorder is entropy. So entropy means disorder. Your bedroom, if it's a mess, is in a high state of entropy, complete disorder. But after you spend some time to clean it up, you can then create order, which sort of leads us to our next point, that if you add energy to a system, you can create order. You can put things in organized ways. Just like you have to use energy to organize your room, you can add energy to molecules and stick them together into larger, bigger, more organized forms. So adding energy means you can create order, which means you can lower entropy. One works the opposite of the other. Losing energy from a system usually means that if the energy is being lost, then that means bonds are breaking and things are falling apart, okay? Which means you are creating disorder. More disorder. You're making things in a more random arrangement. And that means that you are now raising entropy. Now, when I say losing energy and adding energy, there's still energy in disorder, but it's useless energy. That's the catch. So maybe what we should do is go back here and write in adding useful energy or losing useful energy. Because there's a difference between energy that's useful or energy that's just kind of wasted as heat that can no longer be captured back to be reused. Think of it that way. Okay? We sometimes describe useful energy as free energy in a system. It's free energy in the sense, not because it doesn't cost anything, but because, it's available. It's energy that's available to be captured and used. Free energy. So we might want to add here that by free energy, what we mean is energy that is available to do things. Available to be captured, to do something useful. When we talk about physics, we use the word work. The word work means using energy to do something or accomplish something. In English, we kind of use the same word. We use our energy to get work done, clean our room. In physics, work is essentially any time you use energy for anything. So, lifting a cup of coffee, driving a car, whatever, we call it doing work. And of course, we are concerned, this work that we're going to talk about is the work that's needed to organize biological systems and keep them from falling apart into entropy, into disorder. Okay? How are we doing there? Do we need to go back at all? All right. Sure. How about there? Okay, we'll pause for a second. Okay. Now, we have to remember that there's a difference between okay, it's not going to cooperate. Let's go back down. Get my pen again. There's a difference between, yes. All right. I added a D here. This is captured, not Neptune, as some thought it was. I think the context, though, could help you with that. I don't think Neptune would fit in there, right? Okay, so a closed system and an open system. That's an important thing for us to remember. Closed versus open. A closed system is basically sealed off from its environment, so it does not interact with its environment. Interact. That says interact. It does not interact with its environment. And more importantly, what that means is that no energy No energy enters or leaves the system from the outside. I'm not going to write that, but you can add it in if you want. No energy enters a closed system. But an open system is one where energy can enter the system or leave the system. And of course, if you think about biological systems like humans, organisms, dogs, cats, fruit flies, and whatever, they are open systems because they are constantly taking in food and giving off waste products. Right? Biological systems. And again, what does that mean, biological systems? It means organisms. It means pathways of biochemical reactions in cells. It means anything that happens in biology, basically. Biological systems are typically open systems. Open. And that's why they seem, at first, to violate the laws of thermodynamics. The law says that everything proceeds towards more disorder, but a human being is clearly going from a state of disorder towards a state that's more ordered. Any organism it's called an organism for that reason, right? It's organized. So an organism is organized because it's sort of using energy from the outside to create order and sort of fight the tendency to fall apart. As soon as an organism stops obtaining energy from the outside world, it begins to fall apart and it dies. It breaks down. So that is typically open. Biological systems, typically open. Okay, so now there was a guy named Gibbs. And so Gibbs basically studied and this idea of energy that's available to do work, and he did some mathematics to describe it, and so we honor him and we call the free energy available to do work in a system Gibbs free energy, and we use a capital G to describe it. So when you see capital G, think of Mr. Gibbs, and basically remember that's just a way to describe how much free energy is available. Yes? So Gibbs free energy is, I'll summarize this, the energy available to do work. And by do work, what we mean is that there's energy that can be captured and used for some other purpose, even though some of it will be wasted. Okay. And Gibbs free energy is usually measured under sort of constant, it's measured with constant temperature and pressure. Temperature and pressure are complicating the issue because they also change the order of a system. They change the way systems jiggle about, right? The hotter they get, the more they jiggle. So in order to look at the energy available, we have to do it in a way that we hold these variables constant so that they don't mess up our understanding of the free energy. So constant temperature and pressure. Luckily for us, most cells, most biological systems work towards something called homeostasis, which basically is a big word that means being the same, which means they are relatively constant in their conditions. Cells don't like conditions that vary a lot. So they are relatively constant conditions. So Gibbs free energy is useful to us because we are dealing with a situation where the temperature and pressure stays within a very narrow range most of the time. All right. The key thing is that Gibbs free energy, as a measure of this, what it does is it essentially compares the reactants and the products. And it compares how much free energy there is in the reactants. So let me just write it like this. The reactants in a chemical reaction, they do something and they turn into products, right? We know this from grade 9. And you can have many reactants or a few, whatever, and many products. But if we add up the total free energy of the reactants, and we call that, let's call it energy 1 or energy R, and then we add up all the reactants of the energies of the product, their free energies, and we call that energy P for products, what we'll find is that there are a couple of possible scenarios. The first scenario would be that if you added them up and you sort of compared them, you would see that the reactance, ER, was bigger. There was more energy, and then the reactance of the products was less. Okay? And what that would mean is that some energy must have been given off to the environment. Some energy was lost. Or we could also say lost, or we could say some energy was used to do some work. It did some work somewhere. Something was achieved in this process. And so in this case, what we would have is that we would say that the Gibbs free energy, if you think of Gibbs free energy, so the change in the Gibbs free energy, delta G, how much it changes, that would be done by taking whoops, no, I don't need the delta there, hang on. The Gibbs free energy of the products, take away the Gibbs free energy of the reactants, G2 minus G1, right? When we do products minus reactants, like when we do math. And so what would happen in the case of the reactants being bigger, if this was the case, then the delta G would end up being a big number. On the right side, the GR is bigger than the GP. This would be a negative number. That's all we really need to understand. Right? It would be a negative number because GP, actually, you know what I should do is I should have written, you're probably confused because I'm using a G and an E. I'm going to put the G here, then that'll make more sense. Yeah, because I gave you two different letters, right? So the G represents the free energy. So now you can see that this makes sense. The GR is bigger than the GP, so if you subtract a bigger number, you get a negative result. And what that means, of course, is energy is lost and did some work. And of course, we saw that the word we use was to describe that was exergonic. An exergonic reaction or system is one where energy is being lost. In other words, the Gibbs free energy is negative. Now, because energy is doing some work and being lost, what tends to happen is that this reaction will proceed along the laws of thermodynamics. In other words, the amount of order has decreased. Okay? Some energy is lost in this system. So this means that in an exergonic reaction, entropy increases. Oh, I'll try and write that in English. Entropy increases. Energy is released. When you release energy, the products are going to be more disordered. Entropy increases, and that follows the laws of thermodynamics. We said that the universe wants to increase entropy and proceed towards disorder. So that means these reactions proceed spontaneously. Proceed spontaneously. Now, spontaneously is not the same as immediately or quickly. Spontaneously just means that given a little push, these reactions will just carry on all by themselves. So you can imagine a good example is burning a fire, right? You still need to light a match and give it a kick. But once you kick it with the match, the entire fire begins to burn, and it'll burn as long as there's fuel available. It doesn't require any more matches. So that's what spontaneous means. A spontaneous reaction is one that will proceed towards an increasing entropy. It will give energy off in the process. It will be exergonic. And it will be able to sort of go on and on and on and do its thing once it's kick-started. Okay? The opposite of that would be, if I go back here, well, what if I make the opposite statement of this? What if the free energy of the products is actually more than the free energy of the reactants? Well, in that case then, the free energy of the reactants is, no, backwards, is less than, oops, eraser. The free energy of the reactants is going to be less than the free energy of the products. In other words, there seems to be more energy at the end than there is when you started, which means you had to put energy in, right? So this means that energy was added. Energy was added. And this kind of a reaction means that if you're adding energy and the products have more energy, then what that means is there is less entropy in the products. Entropy in the products. So the entropy has, remember, entropy is disorder, so you've become more organized, so the entropy has decreased. Entropy decreases. And if entropy decreases, that means you're becoming more ordered. You're going against the law of thermodynamics that says everything proceeds towards disorder. But the reason you can do that is because you have added energy, right? You've added energy to make this happen. And of course, if you're adding energy, that's like the energy is being absorbed from the environment, and we call that an endergonic reaction. And of course, an endergonic reaction is non-spontaneous. It will not happen or just carry on because it requires energy. And if you stop putting in the energy, it'll just shut down. It's like a fire that requires you to keep lighting a match consistently over and over and over to keep the fire burning. Right? That is non-spontaneous. And of course, the G value, if we go back to that little thing here, if I look at this reaction, then the delta G, the change, which is the products minus the reactants, if the products is a bigger number, this will give us a positive answer in this subtraction. So a positive Gibbs free energy change would mean an endergonic reaction. Okay, we're going to pause there for a second. Okay, so your textbooks and the way that this Gibbs free energy is often written or described is through an equation that says delta G equals, or the change in your free energy is equal to measuring the change in what's called the enthalpy, which is, in a way, sort of describing the total energy of the system. And then temperature times the change in S. S is entropy. So we have here, that's the change, remember delta, the change in Gibbs free energy. This delta H here is it's called the enthalpy. That's the fancy word for it, enthalpy. So when you study chemistry and further on in science, enthalpy and entropy are sort of the two things that we're talking about here. We're basically using enthalpy to describe the total energy of the system. And then this last part over here, well, there's two parts. There's the T, which is the temperature. That's measured in kelvins. Everything in science is measured in Kelvin. Well, not everything, but often. And then this delta S is the change in entropy. S is the letter we use for entropy because they're both E's, and so that would be confusing, right? Entropy. And so if you look at this equation, you can kind of see that what you're doing is you're subtracting the change in the entropy from the change in the enthalpy. You're comparing the total energy and the disorder, and you're just kind of subtracting one and finding the difference between the two, I guess is a better way of saying it. But this is just a sort of a mathematical way of describing everything we've been discussing up until now. Essentially, from this equation, you can see that if the entropy goes up, it makes the term on this side larger. If entropy goes up, if a system becomes more disordered, right, then that would be a bigger number. Whereas if it becomes less disordered, the entropy goes down, that would mean more order. Okay? So you can describe it this way mathematically, but essentially what we're going to be doing is describing it more in terms of how I describe it here, because really all we want to do at this point in time is be able to associate a positive Gibbs free energy with a Endergonic non-spontaneous reaction, right? So if we were to summarize, we would say that a positive delta G indicates an Endergonic non-spontaneous reaction. And the reason is because, it requires an energy input, so it will not just keep on going. Non-spontaneous, a constant energy input, right? Non-spontaneous reaction. And then, of course, a negative delta G would indicate an exergonic spontaneous reaction. And remember that spontaneous means it will proceed once it's gotten going. It needs that kickstart. It doesn't mean that it just automatically happens. It means that it will proceed spontaneously by itself without a constant energy input once you give it that initial kick. Okay, question. Good. So the question was, is it possible that the delta G could ever be zero if they were equal? And of course it's possible, anything's possible, but a delta G of zero would mean that there is no real energy difference between the products and the reactants. So the energy of the products is basically the same as the free energy of the reactants. And so there would be no change, which would essentially mean that there would be no reaction, because what's the point of reacting, right? And so a way of thinking of it, another way of describing all of this, in another sort of analogy, I guess, is to think of it as nature, right, or the universe, is always trying to acquire an equilibrium, which means everything is balanced, right? So if something is going up, something else is going down to balance it. And so the equilibriums are always dynamic, which means there's always things moving, but the net effect of one thing going up and another thing going down creates this evenness, right? And so what life has to do, the purpose of biology then, is in order to have chemical reactions, what life actually does, life consists of organisms that use energy to purposely push things out of equilibrium. Out of equilibrium and utilize the efforts of nature to put it back. The efforts of the laws of the universe. So in other words, the universe has these laws of thermodynamics, and we've discovered that we can temporarily, or at least to a small degree, push them out of balance, and then the world will say, wait a minute, and try to balance it back. And so life is constantly pushing things slightly out of balance and allowing the universe trying to balance it again to get stuff done. So it utilizes the efforts of nature to reestablish that equilibrium, re-establish the equilibrium. So it's really quite clever. And this is why life can exist in a universe that is supposed to be progressing towards disorder. It's because life can temporarily bump things towards order by using energy. The problem is, of course, is every time you do that, energy's lost. And so the efforts of the cell are constantly depleting the energy available to things in the universe. And more of the universe's energy is becoming unavailable every time, which means eventually we'll run out of energy that's usable. And the only energy that's out there will be waste heat energy that can't be captured and used to do anything, in which case life will have no option and it won't exist. So life will come to an end when the universe runs out of available free energy, right? You can think of it like this. If you have, let's say you have, for some reason, some nice little glass made of glass. That's why we call it a glass. Interesting, eh? We name it based on what it's made of. Strange. But this glass is, you want to break it for some reason. Maybe inside the glass, trapped in there, because the lid is sealed, is a $50 bill or something that you want to get out. So what we can do is we can use the laws of the universe to make this happen for us. I can build a ramp, and I can put my glass at the bottom of the ramp. Then I can put a large round rock up here, which is quite heavy. And the laws of, so in order to put the rock up there, I had to lift it with the power of my muscles, which means I had to put energy into the rock. Energy was required by me to get it into this position. So what I've done is I've sort of increased the energy of the rock, which goes against the laws of the universe, because the laws of the universe are trying, what happened there? Are trying to put this rock back where it was. It wants to be in its lowest state. And so the rock spontaneously will then roll down here and smash the glass and release what was inside. So I've sort of made the laws of the universe work for me, right? But to do that, I had to input energy here. I couldn't do it without inputting energy. And of course, how do we input energy? Well, we have to get this energy. What we're going to learn next is how the energy from our muscles actually is created. How did I get the energy to lift this rock in the first place? And that's what we're talking about coming up. So living things purposely put things out of equilibrium so that when nature puts them back, it does something we wanted them to do, we wanted to happen. That's another way of thinking about all of this stuff. Okay. I think we'll call that sort of the end. Well, actually, you know what? Before we do that, I did have an example here, and we have time. So let's look at it from a chemistry point of view. So here's what I have for an example. If we look at glucose, because we're going to be looking at glucose in quite a large amount of detail. C6H12O6 is the glucose. And we know that if we react that with 6 oxygen molecules, we can produce 6 carbon dioxide molecules plus 6 H2Os. This is what we call an overall reaction. And as we're going to learn, it actually doesn't just turn into this immediately. This comes about after a very long chemical pathway with many, many steps, where at the end you get carbon dioxide and water, but there's so many steps in between, right? That's what we have to learn the details of. But if we look at this and we compare the energy, the free energy of these reactants and the free energy of these products, what you'll notice is the products are simpler molecules, aren't they? You can look at those and you can say, they are simpler, smaller molecules. And this glucose molecule up here is quite a complicated molecule, which means it has more order. It has more order. And so this particular reaction looks like it's proceeding from a more ordered state on the left to a less ordered state on the right. Smaller molecules have less order than bigger ones. So if you had to ask, you could identify, maybe just by looking at that, you could suggest that whether this is endergonic or exergonic. If the products have more disorder after they're done, then that would mean you're going from a lower entropy to a higher entropy, which is the opposite of going from energy. That would be going from a higher energy to a lower energy, because the two are opposite concepts. So you could suggest that this is exergonic, right? In other words, if you give it a kick start, it'll go. In fact, if you light a little match to glucose and just let it go, it'll burn like a piece of wood. It's a fuel that can burn or combust. This is a combustion reaction. So we can suggest that this is exergonic. But we can also measure. Now, we're not going to measure in this class all the different actual numbers. But it turns out that if you measure the difference between the products and the reactants, if you take the energy of the, the energy of the reactants, and you subtract the energy of the products, because the products have, actually I think I did that backwards, sorry. Remember it's 2 minus 1, so you always go products, take away reactants. Let's fix that. The energy of the reactants, which is the blue side, and you subtract the energy of the products. I did it backwards again. Sorry, I'm having a little brain issue here today. Must be COVID. The energy of the products, take away the energy of the reactants. So the blue side, take away the red side. Well, we said the red side was bigger. It has more energy because it has less entropy. So EP minus ER. If you do that, you'll actually can measure it and get a number. It's minus 2870 kilojoules of energy for every mole. And the minus means that the energy is released. It's exergonic. So if we burn glucose, apparently what happens in this reaction is 2,870 kilojoules of energy are released as free energy. So all we have to do is capture that, and then we could reuse it to, to have skin cells grow and to have proteins made and to do all the things that living things need to do. And of course, it's measured in kilojoules per mole because everything in chemistry is per mole, right? Because that's the convenient amount that we use. That's all free energy to do useful work. And this, of course, is the work this energy is what cells use. This is the energy cells can apply to endergonic reactions that it wants to happen. Like, remember the smashing of that glass. Things that are going to require energy to happen, like growth and the building of bigger molecules, like lipids and fats and things like that. So this energy is what's available. So what we have to learn next is essentially how we can get that free energy captured. And of course, the way we do that is by utilizing a very important molecule that you've already heard about, and that'll be the start of the next video, and it's the molecule of ATP, which is the sort of energy coupling molecule that links the exergonic reactions of glucose being burnt to other reactions in the cell that allow us to build things. In other words, these other endergonic reactions are the things the cell is doing to push nature slightly out of equilibrium, like lifting the ball, the rock, up on the ramp so I could smash the glass, essentially. That's the idea. And of course, that's done by coupling, but that will be the next video, because this one's gone on long enough. So we'll stop there. That's our little, the end of talking about energy and Gibbs free energy. The takeaways from this, of course, are this little summary that we wrote up here. I'll go back to it right here. This is sort of what we want to make sure we can understand, and also how we can make sort of generalized kind of looking at, say, this equation right here. You can recognize where there is more disorder and where there is less disorder by the sizes of the molecules. And then you can make an estimate as to whether or not it's endergonic or exergonic. You don't have to do the actual measuring or memorize this number, but I just put it there as an example to show you, right? So that's basically the takeaway from today's lesson.